Welcome back, friends. Here we are going to deal with the simple harmonic motion, and we are into the fourth quarter. In this fourth quarter, we are going to talk about forced oscillations and resonance. In this fourth quarter, we are going to discuss forced oscillations and resonance. We are going to roll through introduction, then forced and natural vibrations, analytical treatment to the problem. Then we are going to discuss resonance when the vibrations, the time period of forced vibrations and time period of natural vibrations is identical, then the phenomenon of resonance takes place, that we are going to understand in terms of the analytical treatment equations. Then we are going to talk about resonance and its sharpness, power absorption by the mechanical system, then velocity of resonance, bandwidth, and quality factor. Here, consider a person swinging in a swing without anyone pushing it, without any external force playing into it. Then this makes an example of free oscillation. Now, instead of a person, you imagine a dead object which is swinging, because a person can swing himself while sitting in the swing. So it's better to imagine an object instead of a person which is swinging without any pushing. That's a case of free oscillation. We have discussed this in earlier quarter. However, if someone pushes the swing periodically, like another person is swinging his friend, then the swing has forced or driven oscillations. So this is forced oscillations or driven oscillations, one can say. Two angular frequencies are associated with the system undergoing driven oscillations, which the natural frequency and the frequency caused by the forced or driven oscillations. The natural frequency, here we go, natural angular frequency omega of the system, which is angular frequency by definition, at which it would oscillate if it were suddenly disturbed and then left to oscillate. So that offers you natural frequency, which we have widely discussed in earlier three quarters. Now we are interested in the external driven force. I have underlined this D so that I'm giving a suffix to omega, that is D, which is a driving force that is imposed by the external force to cause angular frequency. So here we have two frequencies, omega because of natural oscillations, I mean angular frequency of natural oscillation, and angular frequency of forced or driven oscillations. So WD, D is reminding us that it is the external driven force that is causing the oscillations. Now, forced and natural vibrations, where the oblique doesn't mean that one is either and another is or. We are talking about forced vibrations or oscillations, and we are talking about natural vibrations and natural oscillations. So natural oscillations has natural frequency omega, while the forced oscillation, which is driven oscillations, that is omega t. When these two frequencies are identical, then the phenomenon of resonance occurs. So by definition, I want to state that when the period of vibration, see here, I want to mention that omega is equal to 2 pi upon capital T. Capital T is the period. So the period is related to omega. So, or otherwise, one can prefer to write T is equal to 2 pi upon omega. So I can either talk about omega or I can talk about T. It does not matter, but they are inverse of each other with the constant of proportionality 2 pi. When the period of vibrations caused by the external driving force is equal to period of natural vibrations, this leads to a phenomenon of resonance. So we have the phenomenon of resonance when these two frequencies are equal. External force will set up oscillations. The external force which we are providing is definitely bound to set up oscillations, but the body will tend to vibrate, will tend to oscillate with its natural frequency. It means that even if we impart different frequency, we impart this frequency, but the body will tend to attain this frequency when they are different. But when they are same, resonance will occur. Applied force, in fact, helps the motion. So it has to be in the phase, definitely. Otherwise, it will act against. So applied force helps the motion, or sometimes it opposes the motion. So we have to take care of what role that force is playing. You have to synchronize the things. This helps or opposes factor will decide the amplitude. If the force opposes, then the amplitude will diminish, it will go down. If the force helps, amplitude of oscillation will increase and it will tend to oscillate with the natural frequency. So this omega natural frequency will take over omega t. Now friends, we are in position to understand the analytical treatment to forced oscillations. Suppose that the body undergoing oscillations has mass m and the period, as I said, because of the external force, it will be 2 pi upon omega d. So external force will oscillate with the angular frequency omega d, and t represents the period because of forced oscillations. Now under the action of external periodic force, the force that we are applying is periodic. F is the force in Newton multiplied by sine of omega d t. So here we are enforcing the sinusoidal force which causes the periodic motion, and that periodic motion is we are discussing forced oscillations. Now friends, this is the fourth lecture, and in the earlier lectures we have discussed this term R into dx by dt, where R is the kind of resistance, opposition to the motion is involved, and this resistance is proportional to velocity. When velocity becomes zero, this factor becomes zero. When velocity is highest, this factor is highest. This represents damping force. We have done this in one of the earlier lecture. Now displacement I'm writing in short. In fact, this displacement I should write as this is x of t, where x displacement is function of time, but I'm preferring to write this as x. You have to remember that x is a variable that parametrically depends upon time. Now, this is the differential equation of motion that we have already discussed somewhere in one of the earlier lectures. M into this factor is A. This is force equal to force. This time force is sinusoidal force, plus R into dx by dt. This is a kind of damping force, and the oscillatory motion which is coming into picture is represented by k into x. Here I presume that you have followed this equation, which is outcome of earlier 3 lectures. Now we can divide this equation by m. So when we divide this equation by m, this m will be eliminated. We are left with r by m. Here it is appearing, and this will be k by m, and here it will be f by m. So I should have small f here, where this small f is equal to capital F upon m, that is force per unit mass. So this is our differential equation, which we would like to mend into a standard format and would like to go for the standard solution. Now here in this equation we have r upon m, we are replacing by twice p. Then k upon m we are replacing by omega square, and capital F upon m we are replacing by small f. So we have this as a standard form of the differential equation, and the period of forced oscillations t is 2 pi upon omega d. This is an important thing you should remember. We are going to explore this in the forthcoming discussion. The solution to the above differential equation is simple. We have done that, and that is x of t is equal to a, which is amplitude of oscillation, into sine of omega d. Here omega d is all the way involved. So in earlier solutions we have used omega. We were talking there about the natural vibrations. Here we are talking about the forced vibrations. Therefore omega d into t minus theta. So theta is the phase angle involved. As I said, a is amplitude, omega d is the angular frequency of oscillations, and theta is the phase difference between external driving force and the displacement. So it all depends upon the phase. If the force is not in phase, this can be 0. Omega t minus theta can be 0, and if that is not in phase, this whole thing will result into sine of 0. Now we have this differential equation, and this one is the solution to the differential equation. Now we are going to handle this in a collective way so that we can find the significant treatment and then further analytical explanation, analysis for the whole situation. So here we have x of t already known, and then we have to substitute that at this place. Okay, then we need dx by dt. We need to find out this. So to find out this, we need to differentiate this equation once with respect to time, and that is being carried out here. and the first derivative is like this. Now I'll not explain you how this derivative is evaluated. You are grown up now to understand that derivative of sine of a function is cos of function into derivative of the function. Then we have to have second order derivative. So when we are interested in the second order derivative, we have to work out this quantity and replace it with this quantity. So in all, we have substitution for, let me highlight that, we have to substitute second order derivative, first order derivative, basic solution right from this equation, and this pair which is obtained out of derivative. If we substitute that, then we have all the values being substituted here, and here we have a clumsy equation where we have to have on right hand side force f, small f, into sine of omega d t. Now this equation holds true for all values of t. It means that at any point of time this equation is valid. Hence we are going to equate the coefficients of sine and cosine. Before that, we have to address something for right hand side. Now sine of omega d t, f times, we are writing as f times sine of omega d t minus theta plus theta. So here we are going to treat this as alpha plus beta. So sine of alpha plus beta is equal to sine of alpha cos of beta plus cos of alpha sine of beta. So here we have to equate sine components on both the sides. So here I have underlined the sine components on left hand side, and this equation is right hand side. What are the coefficients, cosine components? The cosine components are underlined with red underline. And what are the coefficients of sine? So coefficient of sine, I shall try to highlight with this yellow shade, minus a omega d square plus omega square a square, and this is equal to f times cos of theta. So this is the coefficient of sine of omega d minus theta. So here omega d t cannot be equated, so we have adjusted theta so that we can equate sine components appropriately. Then we want to equate the cosine components, and I shall try to highlight now the cosine component. What color I should prefer? I'll prefer this one. So here 2ba omega d is the component of cosine on left hand side, and on right hand side we have f times sine of theta. So I can write a pair of equation by this comparison, and this pair of equation, this is the first equation which is obtained out of sine coefficients comparison, and this is after cosine components comparison. Now these are the two equations we have just now discussed, and here we have solution, that is sine of a times sine of omega d t minus theta is the instantaneous displacement. Now here we can take a ratio of two equations so that later equation divided by former we can obtain tan of theta, and similarly we can rearrange this equation for amplitude. So if we try to arrange for amplitude, 2b omega d goes in the denominator, and the numerator we have f sine theta. So this is how we obtain tan of theta, and amplitude. Now, we shall explore the amplitude in this basic equation, which we are calling as solution of the forced oscillations. So here we have replaced A, that is amplitude, by this quantity. Now that is multiplied by sine of omega d minus theta. Now squaring and adding first pair of equations. So this equation I'm going to square so that on right hand side I have f square cos square theta. I'm going to square this equation. On right hand side I have f square sine square theta, and when I add them together, sine square theta plus cos square theta is equal to 1. So on right hand side we have, this should be f square. We have f square on right hand side, and on left hand side we have a square omega square minus d omega d square plus 2ab omega d whole square. Now this equation can be further rearranged to obtain amplitude, and this time we have explicit representation of amplitude in terms of force, in terms of natural frequency, in terms of forced vibrations frequency, in terms of B, which is a constant we have obtained out of some substitution in the earlier slide, and again omega d square. So here we have x of t, which is equal to a sine of omega dt minus theta, where a is being represented like this. And the full complete way of representation of displacement, which is the gist of this analytical treatment, is this very equation which is highlighted on your screen. Our exactly applied force is a periodic, and damping force is continuously prevailing in our system. Because resistance we cannot make zero, we can minimize it, but in natural systems we are discussing about the damping force prevailing. Therefore, we shall add to the above equation the solution of damped vibrations from our earlier lecture. So here I am rewriting the instantaneous displacement of the system x of t, and this is composed of two parts. Now I am talking about the second part, which we have discussed in the earlier section, where y I am writing as the amplitude, that is multiplied by e to the power minus bt, where this b is the damping factor, and y into e to the power minus bt, this becomes in fact amplitude. Now if you will try to realize what is happening to the amplitude, only amplitude part as a function of time, I'm talking about only this portion, then at t equal to 0 we have maximum amplitude, and as t increases the amplitude will exponentially decay and will have asymptotic behavior with your x-axis. In addition to this, it is being multiplied by the factor sine of beta t plus phi. This equation we have derived in our earlier section. In addition to this, we have the first part y0 that we have developed in this section into sine of omega dt. The driving force is causing omega d, and that is multiplied by t. So the angular frequency omega d is caused by the driving force minus theta. So here I want to mention that y0 is the amplitude and that is multiplied by sine of omega dt minus theta. So here your displacement is sum of two parts. This part is because of the earlier section that we have discussed regarding damped oscillations, and this part is because of the force which has taken place into the system, and this article we are discussing for forced oscillations. Now here I would like to remind you of beta, and beta is under root of omega square minus k square. I shall remind you about omega and k. However, at this point omega I will say as the natural frequency, and this omega d is the frequency because of the driving force. So this is equal to omega square is k by m. Now we are talking about beta and it is in the under root of omega square minus k square. So omega square is k by m and k square is r square upon 4m. So this we have picked from the earlier quarter. So this is what is the meaning of beta is, and I want you to understand this, that this is in the under root. So this under root sign is somehow missing, so I am redrawing it. Then we have y which is prevailing here. So this y we are talking about, that is equal to ay0. So here small y suffix 0 is the actual amplitude of the oscillations ay0 upon beta. Capital Y suffix 0, I'm talking about this part, and this part is prevailing here. This y0 just now we have established it is equal to F, that is force per unit mass, divided by under root of omega square minus omega d square whole square plus 4b square omega d square. So this we have established. Now what we have done, that we have combined the natural oscillations part and under damping condition and forced oscillations part. So this is how we have had an equation comprising of two sinusoidal terms, different amplitudes, one amplitude expressed like this, another amplitude, first amplitude expressed like this, second amplitude expressed like this. Now here one should observe that the damping factor is e to the power minus pt. So in our equations it is prevailing at this point. So this is causing exponential decay. Here you can see that the amplitude is diminishing exponentially fast. Now this causes exponential decay in the amplitude that we have understood. Then 2 pi over d. This factor represents period capital T, and this is because of the driving force, period because of driving force, and the amplitude y0 here I have rewritten, which is actually not necessary. Now initially the body oscillates with the period 2 pi over beta or 2 pi over omega, whatever you say, and the external force tends to oscillate with the period 2 pi or omega t. So in reference to the article that we have discussed earlier, this factor was 2 pi. Upon omega, you can consider 2 pi upon beta. The simple harmonic motion thus depends upon the competition between omega d and omega. That is, angular frequency because of natural vibrations and angular frequency because of the driving force. So how the competition between these two omegas take place, it depends upon that. So here I have rewritten the equations for x of t, and the meaning of y0 is as appearing on the screen. Now here we are interested in talking about the resonance and the sharpness of resonance. Now, as I said in the earlier slide, that simple harmonic motion depends upon the competition between omega d and omega. When omega d is large, this quantity is very, very large. See, omega d is large, so omega d square will be larger as compared to omega square, and square of that, so negative factor does not affect because we are taking square of the bracket. So this is large, and the large quantity is prevailing in the denominator. So y0 will become small. Same thing will happen if omega d is very, very small as compared to omega. Then also this quantity will not be negative, this will be positive and it will be large. And as something in the denominator is large, then y0 is small. Now we shall be interested in the resonance phenomenon, and the resonance phenomenon is occurring when omega d and omega, they coincide, they become identical, approximately close. Then the difference between omega square and omega d square whole square, this is tending to zero, nearly zero. Under that situation, uh, this quantity, I want to highlight it separately now. Now this quantity is becoming zero. This is becoming zero. So we are left with only this part, and the large contribution is withdrawn from the denominator addition, and therefore y0 will be f upon 2b omega d, which will be the maximum value possible for the amplitude y0. Now the whole issue is governed by this b, because omega d we know that is equal to natural frequency. The frequency, angular frequency, because of the driving force is equal to natural frequency. 2 is a constant quantity, f is the force involved. The only different parameter in this equation is b, and b is the damping factor, and the damping factor will now take over the issue. If the damping factor is 0, then y0 will be infinite, and if the damping factor is large, y0 will be small. So the whole story in this situation of resonance, what is the situation of resonance? We are talking about natural vibration frequency is equal to the forced vibration frequency. Under that condition, the whole story is governed by B, and it depends whether B is large, then Y0 will be small. If B is 0, Y0 will be infinitely large. Now here you can see, I want to first mention that the listed factors, I'm talking about these factors 0, 1, 0.2, 0.5, 1. These are appearing here as zeta. This diagram I have picked from internet, and in fact I want to chart them as the damping factor B. So when B is 0, what is happening? When B is 0, we are getting maxima. So this is the line pertaining to B is equal to 0. So this is shooting up, and this makes the function actually going to infinity, making it discontinuous. On x-axis, mind that on x-axis I'm plotting omega upon omega d. When omega is equal to omega d, this is the situation for resonance. And omega upon omega d, this will be 1. So the condition of resonance 1 on this x-axis corresponds to resonance. So value of omega upon omega d corresponds to resonance. When this B increases a little bit, say by 0.1, then this is the graph for 0.1. Then when B is equal to 0.2, so your amplitude of oscillation, this is decreasing as the damping factor is increasing, and when B is equal to 1, I'm talking about B, then this is almost flattened. So this is a kind of normalized graph as we are plotting omega upon omega d along x-axis and amplitude on y-axis. Now, rather, this should be y0. Now here we have x of t rewritten, and y0 we are writing since so many slides. So here some overwriting makes it clumsy. When omega d is equal to omega, this factor becomes 0, and here this quantity vanishes. So y0 is equal to f upon 2b omega d, which is maximum, and it is governed by b, and b is in fact r upon 2m, where r is the coefficient of resistance. Now if resistance is 0, then this condition arrives, and we are talking about this graph shooting up to infinity. So for B is equal to 0, the amplitude is maximum but not infinite. Mind that. Energy is repeatedly supplied to the system with no loss. So when the oscillations are taking place, when the body is in the extrema, that is on the extreme ends, then the potential energy is maximum, kinetic energy is 0. And when the body is in the mean position, then potential energy is minimum and kinetic energy is maximum. So this dancing of energy between potential and kinetic smoothly, it occurs repeatedly without any loss of energy. So this causes resonance. Now we shall discuss power absorption. Now x of t we are writing as y0 sine of omega dt minus theta, where y0 is represented like this, and you know all these terms. This is force per unit mass, natural frequency of vibration, frequency because of the driving force, v is the damping factor, and same parameter. Now we shall expand this as sine alpha minus beta. So this will be y0 sine of omega dt cos of theta plus y0 cos of omega dt into sine of theta. So here I am writing the coefficient of sine theta. The coefficient of sine theta is y0 cos of theta, and y0 cos of theta I am writing as A elastic, AEL. Later on I am going to shorten it to AEL. And then coefficient of cos of omega t is y0 sine of theta. So this is A absorption. Now A elastic into sine of omega t is in phase with the driving force, while A absorptive force, A absorptive into cos of omega dt is out of phase with the driving force, because sine and cosine components are normal to each other. So one is in phase, another is out of phase. The instantaneous power at the input to the body is P in into the instantaneous force multiplied by instantaneous velocity. Force into velocity is power. So this is the force. We already know that the instantaneous force is F sine omega dt, and the instantaneous velocity can be obtained by differentiating x with respect to t, where we can consider x from this equation. Now F sine omega dt into, so this I have written as it is, and dx by dt I want to write. So A elastic into derivative of sine omega dt will be cos omega dt into omega d. So here derivative of sine omega dt is equal to omega d into cos of omega dt. A elastic is in fact y0 cos theta, and differentiation with respect to time will not matter amplitude and cos of theta. They are independent. Then we have to differentiate cos of omega dt. Derivative of cos of omega dt will be sine of omega dt into omega d into A absorptive. So P average will be equal to 1 upon time period into integration P in dt. So we are integrating the instantaneous power with respect to time over a complete cycle. So t will roll from 0 to capital T. So 1 by t is common. Here in this equation, F into Wd is common. So here you can identify. I'll try to highlight this for you. F is here, then omega d is here, and omega d is here. So F into omega d I have taken out of the bracket into A elastic integration sine of omega dt cos of omega dt dt plus A absorptive into sine square of omega dt dt. Now P average, we have already started with this. This I am writing again because it should be in continuation. And here this integration sine theta into cos theta dt, d theta rather, where theta rolls from 0 to t is 1 by 2 sine of 2 theta d theta. This is equal to 0. Then the integration sine square omega dt, this amounts capital T by 2, half the period. So P average is equal to 1 by T F omega d. First part is 0, second part is T by 2, that is multiplied by A absorptive. Now this can be further simplified as 1 by 2 F omega d A absorptive. Here we are cancelling this T in the denominator with a T in the numerator. And then we are going to write A absorptive, which is in form of this very equation. Now at resonance, omega d is equal to omega, and when we substitute omega d equal to omega, then this quantity becomes 0, and we are left with only this part in the under root, which is 2b square omega d square. And P maximum will be 1 by 2 f square upon 2b. So here this 4 in the under root will amount to 2, b square will amount to b, and omega d square will be cancelled with this omega. And this will be the maximum power involved, and for no damping you have to consider B to be 0, and the moment you consider B to be 0, this power will tend to infinite large value. Now the infinite large value of amplitude, it corresponds to intolerable large amplitude. This is called as resonance catastrophe, and the constituent of the body will be detached and will break into pieces at the resonance catastrophe. Now we are in position to discuss the velocity of resonance. The velocity of the amplitude we have to set up. V0 is equal to A into omega d. Now omega d I have written, and A is replaced by f upon under root of this long term. If omega d is increased from certain small value with respect to w, so you have to identify one value of w, and we are starting with w0 as a variable quantity, and it is approaching to w, rather omega. So the value of v0 will increase till it reaches maximum at omega t equal to omega, which is the condition of resonance. Now here tan of theta, you have to refer to the earlier equation where we have established sine theta cos theta, and we are taking a ratio of those two equations to identify tan of theta, and that amounts to this value, 2b omega d upon omega square minus omega d square. At the resonance, the denominator will be 0 and the value will be infinite, and the corresponding theta for tan function will be pi by 2. The phase difference theta is equal to pi by 2 prevails between the external force and the instantaneous velocity. Now we are here in position to discuss the bandwidth and the quality factor. At the resonance, we have omega d is equal to omega, and the period t is equal to 2 pi upon omega, or 2 pi upon omega d, because omega and omega because omega and omega d, they are identical. And that corresponding frequency, natural frequency, regular frequency, not angular frequency, f is equal to omega d upon 2 pi or omega upon 2 pi. Now here Q, quality factor, is frequency of resonance upon the bandwidth. And here we are considering Fr as the frequency of resonance. In terms of angular frequency, I'm writing here. So if you like to turn this value in form of F, then what all you have to do is divide this quantity by 2 pi, and that will make you to reach to F. So this is the maximum amplitude, and the corresponding value is omega 0. I propose this to be frequency of resonance. So you can call this as Fr. And to obtain Fr from omega, we have to multiply this quantity by 2 pi. Now, bandwidth, we are talking about the amplitude which has maximum value. You have to divide by root 2, that is 0.707% of 0.707 times maximum amplitude. So it has two corresponding frequencies, and one is omega 1 corresponding to F1 and omega 2 corresponding to F2. So from these numbers you can identify Fr, that is resonance frequency, F2 and F1, and you can calculate the quality factor for the given mechanical system. Thank you for your patience.